Hello everyone, my name is Ksenia Yadav. I'm the Director of Data Engineering and AI ML at Enablers Technologies, and this is a tutorial on machine learning fundamentals with applications in photonics. Machine learning is a wide and rapidly evolving field. It encompasses a vast array of techniques, algorithms, and methodologies that enable computers to learn from data and make intelligent decisions. What makes ML particularly exciting today is the constant stream of breakthroughs and advancements that are reported almost every week. These breakthroughs span a surprisingly diverse range of applications, from healthcare and finance to robotics and natural language processing. It is truly awe-inspiring to witness how machine learning is reshaping industries and transforming the way we interact with technology. Our goal today is not to go very deep into any particular aspect of machine learning, but to create a cohesive picture of the entire machine learning landscape. There are some excellent papers and presentations that describe the advancements of ML in photonics and in other domains. It will be their goal to go deep into particular applications, but our goal for the next hour will be to create more of a navigational map of the entire landscape. We'll begin with an introduction where we'll first talk about machine learning categorization, then describe some high-level concepts, and then talk about evaluating models as well as the software and hardware requirements for ML development. We'll then go into classical machine learning, and here we'll talk about support vector machines and random forests. And lastly, we'll talk about deep learning, and here we'll describe artificial neural networks, data augmentation, transfer learning, and then briefly talk about transformer networks and reinforcement learning. Artificial intelligence refers to the broader concept of creating machines that can mimic human behavior and perform tasks that typically require human intelligence. It encompasses various techniques to enable machines to exhibit intelligence by simulating human cognitive processes such as reasoning, problem solving, perception, and learning. Now, machine learning, which is a subset of AI, is the science of programming computers so that they can learn from data. In other words, it's a field of study that gives computers the ability to learn without being explicitly programmed. And deep learning, which is a subset of ML, utilizes artificial neural networks, a very simplified model inspired by our cerebral cortex, to facilitate learning and enable sophisticated pattern recognition. Now, over the past few years, deep learning has overshadowed classical machine learning techniques, and for very good reason. Deep networks achieve performance far beyond that of classical ML methods in many domains, and they scale very effectively with data. However, as we will discuss again and again, deep neural networks require extremely large amounts of data for training. And in many practical cases, such large data sets are not readily available and will be expensive and time-consuming to acquire. Classical machine learning techniques work better when the data sets are smaller. Also, classical ML techniques are not very computationally expensive and thus do not require the best hardware, so it's definitely a cheaper alternative. And in many cases, results from classical ML techniques are easier to interpret compared to the black box that are deep neural networks. So for these reasons, today we will cover both classical ML techniques and deep learning. Machine learning can be categorized into three broad categories: supervised learning, unsupervised learning, and reinforcement learning. Each of these represent a distinctly different approach to acquiring knowledge and making predictions. Supervised learning is a machine learning paradigm where the model learns from a set of labeled examples. The intuitive analogy here is of a student that learns from a teacher who presents numerous examples along with their expected solutions. Each of the labeled examples is called a training instance, and together they form a training set. Supervised learning is divided into two types of tasks: classification and regression. So here's a simple classification example. The training set consists of a variety of shapes and their corresponding labels. During training, a model learns from these labeled examples to recognize patterns and relationships between the input features, which are the shapes, and their corresponding classes. Now, once the model is trained, we can feed it a shape as an input, and it will use its knowledge to classify it into the appropriate category. Now, more advanced classification application would be medical diagnosis to predict multiple conditions based on patient imaging data. So the model can be trained to simultaneously predict the presence or the absence of different diseases, allowing for multi-label classification. Unsupervised learning represents a different paradigm, where the training data lacks any explicit labels or annotations. The analogy here is learning without a teacher, where the model explores the data on its own to discover underlying patterns and structures, perhaps organizing the data into clusters or representations, or uncovering novel perspectives. So here's another simple example. This time the model is given a set of unlabeled shapes. It then discovers hidden structures or patterns in the data. It does so without any prior knowledge of the categories, but it clusters them in some meaningful ways, perhaps by color, by size, by shape, and so on. Because we allow the algorithm to roam freely within the data and to identify these relationships based on the inherent structure of the data, we might get new insights in the process. A more realistic example of unsupervised learning would be to look for trends and correlations within a large amount of high-dimensional data in a manufacturing plant. Reinforcement learning is yet another paradigm which is inspired by the concept of learning by trial and error. In this paradigm, an autonomous learning system interacts with its environment, making decisions and receiving rewards or penalties based on its action. As an intuitive analogy, this can be compared to the way humans learn to play a game by trial and error, exploring various actions, observing the consequences, and developing a better strategy over time. A typical cycle of reinforcement learning includes a software agent which makes observations, takes actions within an environment, and in return receives rewards, trying to maximize its expected rewards over time. So this can apply to playing a game, training a robot, developing a control system, investment decisions, recommender systems, and so on. So while the goal of supervised and unsupervised learning is to find patterns in data and make predictions, in reinforcement learning, the goal is to find a good policy. Now, a few important high-level concepts and definitions. So when we talk about model selection, we refer to the process of choosing the most suitable model architecture and configuration for a given task or data set. So in classical machine learning, it could be choosing a linear regression model or perhaps a polynomial regression model. And in deep learning, it could be selecting a particular architecture and all its parameters that result in a model with good performance. When we talk about training a model, we refer to teaching a model to learn patterns from a set of examples, with the goal of using this model to make predictions. So the learning algorithm searches for model parameters that minimize some cost function and therefore provides the best fit for the training data. Inference refers to the process of applying a model to make predictions on new cases. And when we talk about generalization, we refer to the model's ability to adapt properly to new, previously unseen data. So when we train a machine learning model, we don't just want it to learn to model the training data. That's a prerequisite, but that's not the goal. The goal is for it to generalize to data it hasn't seen before. However, the ability of a model to generalize well to unseen data is not guaranteed, and that brings us to the no free lunch theorem, which states if we make no assumption about the data, there is no model that is a priori guaranteed to work better. The only way to know which model works best is to evaluate them all. In other words, there is no one-size-fits-all machine learning algorithm that performs optimally across all possible problem domains. So this theorem implies that we need to be able to very effectively evaluate and compare the performance of different models. But how would we go about doing that? Well, the only way to know how well a model will generalize to new cases is to actually try it out on new cases. So the most basic approach is called holdout validation. It splits the available data into two parts: the training set, which is the majority of the data, and the test set. During training, the model is only exposed to the instances within the training set, and that allows us to calculate the training error. Now, only when we want to evaluate the performance of the model, we expose it to the instances within the test set. And that allows us to calculate the generalization error, which gives us an estimate of the generalization performance of the model. Now here there are three cases that can give us a good indication of how the model is performing. So the first case is when the training error is high. And that is an indication of an underfit. In other words, the selected model is too simple to capture the structure of the data. In the example shown here, we've chosen a linear model where the data is clearly nonlinear. And the solution is to choose a more powerful model with more parameters. Now the second case is when we have a low training error. In other words, during training everything looks great, but the moment we expose the model to instances within a test set, so cases that it hasn't seen before, the generalization error is high. And that is an indication of overfitting. If the training set is too noisy or too small, the model is likely to detect patterns in the noise itself, which does not generalize to new instances. So overfitting occurs when the model is too complex relative to the amount of noisiness in the training data. And the solutions here are one, to try and simplify the model, two, to reduce the noise in the training data if possible, or to gather more training data. And of course, the goal is to achieve both low training error and low generalization error, which will indicate both a good fit to the training data and good generalization performance. So this is the main idea of holdout validation, but there is a better way to evaluate the performance of the model, and that is called cross-validation. Instead of dividing the data into a training set and a single test set, the data is divided into n subsets, also called folds. And then the model is trained n times, each time selecting a different fold as the test fold and training on the remaining n-1 folds. Each evaluation run results in a score, which is then average. The end result is that we get a much better estimate of the performance of the model than with a single test set. Another way to evaluate a model is to look at its learning curves. So this allows us to observe the machine learning model as it progresses through training, and look at the evolution of both the training error, shown here in red, and the generalization error, shown in blue. And here again we have the same three cases. So if we get a high training error and a high generalization error, it's an indication of underfit. If we get a low training error and a high generalization error, it's an indication of an overfit, and we want to get to a point where both the training error and the generalization error are low, which indicates a good fit to the training data and good generalization performance. Very often, the causes of limited model performance in machine learning have to do with data. So first, we could have non-representative data. It might sound obvious when I say that training data must be representative of the new cases we want the model to generalize to, but in practice, this could be challenging. If the data set is too small, it is subject to sampling noise, and data set of any size can be subject to sampling bias. And that's an entire discussion on its own. Two, we can have poor quality of data. If training data contains errors, large number of outliers or noise, it becomes harder for the algorithm to capture the structure of the data in any meaningful way. So cleaning of training data is often a major effort. Three, we could have irrelevant features. It is critical to come up with a good set of features to train on. And this is an entire subfield of machine learning called feature engineering. And then we have underfitting and overfitting of the data that we already talked about. So here we have to strike a balance between choosing a model that is neither too simple, which would lead to underfitting, nor too complex, which would lead to overfitting. About 20 years ago, there was a well-known paper published by Microsoft researchers who compared the performance of various models on a complex problem of natural language disambiguation. What they saw was that various models, including some fairly simple ones, performed almost identically once they were given enough data. So in many cases, rather than spending time and resources on algorithm development, it may be worthwhile spending the same resources on improving the quality and the quantity of the training data. So today we'll go through a fair number of examples of machine learning applications. Implicit in all these discussions is the fact that the majority of effort was spent on collecting, pre-processing, cleaning, mitigating biases, and other ways of handling data. Especially in deep learning, the most common challenge is overfitting of the data. So to wrap up this discussion and to emphasize this point, let me share with you a wonderful quote by the mathematician John von Neumann, which was later augmented by the ML expert Aurélien Guéron. With 4 parameters, you can fit an elephant. With 5, you can make it wiggle its trunk. With thousands of parameters, you can fit the whole zoo. Machine learning models, especially deep neural networks, have tens of thousands or even millions of parameters. So this gives them great flexibility, but also makes them highly susceptible to overfitting. And now let's spend a couple of minutes talking about the software and hardware requirements for ML development. Today, the most dominant language for machine learning development is Python. Other languages like R, Java, Scala, Swift, and MATLAB also have their own ML libraries and frameworks, but the wide and open ecosystem of Python, as well as its compatibility with other programming languages and tools, makes it by far the dominant language for ML development. Scikit-learn is a very popular machine learning library in Python that provides a range of algorithms and utilities for various tasks, including data pre-processing, model training, and model evaluation. Now, TensorFlow is an open source, comprehensive ecosystem for building and deploying machine learning models, including deep neural networks. It was developed by Google and supports many programming languages, including Python, Java, C++, and JavaScript. An alternative to TensorFlow is PyTorch. It is another widely adopted deep learning framework. It was originally developed by Meta and is primarily intended for Python development, although it also has a C++ interface. Both of these frameworks offer similar capabilities when it comes to ML and deep learning architectures. Both also offer GPU acceleration and distributed computing capabilities. At this particular point in time, TensorFlow seems to be more popular in large-scale production environments, while PyTorch appears to be more popular in the research community. However, both of these frameworks are extremely capable and fast evolving, so the choice between them really depends more on personal preference and existing ecosystems. And the last framework that I will mention is Keras. Keras is a library that acts as a high-level interface for TensorFlow, and it makes it much simpler to train, build, evaluate, and run neural networks. So Keras can be used for the majority of use cases, but lower-level Python API is useful when some extra controls are needed. Now, a few words about hardware requirements for ML development. All machine learning frameworks can run on CPUs. And in fact, CPUs are sufficient for many classical machine learning methods, as well as small-scale experiments and prototyping. Now, for complex models and large data sets, training times can become prohibitively long, and that's where you should start considering GPUs or specialized hardware accelerators. Now, GPUs are graphics processing units, and they're highly efficient for training deep learning models due to their parallel processing capabilities. And TPUs, tensor processing units, are specialized hardware accelerator that were developed by Google specifically for deep learning workloads. And they provide even faster training times compared to GPU. Now, other companies also offer their own AI hardware accelerators, which are more generally known as NPUs, neural processing units. So it's worth noting that while GPUs and TPUs can greatly speed up training, they may not be essential when starting out or working on smaller scale projects. Also, many companies offer cloud-based solutions that allow you to utilize their infrastructure for training models without requiring high-end hardware locally. Now, this concludes the introduction, and now we can begin talking about the different machine learning algorithms. The first classical machine learning algorithm that we'll talk about is the support vector machine, or SVM. It's a powerful and versatile machine learning model that is capable of performing both linear and nonlinear classification, regression, and outlier detection. Let's take a simple classification example where we have two linearly separable classes, the blue class and the yellow class. The three lines shown here represent the decision boundaries of three possible linear classifiers. All three work perfectly well in this particular case, but if you look closely, you will see that the decision boundaries come so close to some of the instances that these models are not likely to generalize well to new cases. Now compare this to the decision boundary of an SVM classifier shown on the right. The decision boundary not only separates the two classes, but also stays as far away from the closest training instances as possible. You can think of an SVM classifier as trying to fit the widest possible street between the two classes. Now, this decision boundary is fully determined or supported by the instances located on the edges of the street. These instances are called support vectors and hence support vector machine. Now, of course, some data sets are not linearly separable, but SVM can also efficiently perform nonlinear classification. So here the approach is similar to polynomial regression, where we handle a nonlinear data set by adding polynomial features, which in some cases can result in a linearly separable data set. However, the problem with polynomial regression is that for complex data sets, this approach requires a high polynomial degree, which creates a huge number of features, making the model too slow. Now, SVMs can perform a nonlinear classification much more efficiently using what is called the kernel trick. We won't go into the details of the kernel trick, but we'll only note that the concept remains the same. The inputs are implicitly mapped from the original finite dimensional space into a much higher dimensional space, where the separation between different classes becomes easier. So this is an example of nonlinear classification using a polynomial kernel using SVM. Now, SVM can also handle regression, and here the trick is to reverse the objective. Instead of trying to fit as wide of a street as possible between classes, we will try to fit as many instances as possible on the street, trying to minimize the number of margin violations. So this is an example of linear regression and nonlinear regression using SVM. So where can SVM be used in our area of photonics? Well, the first example that I'll show comes from our own work at Ensemble. We design and manufacture photonic integrated circuits for various applications including LiDAR, datacom, and telecom. Now, a typical 6-inch production wafer contains hundreds of optical devices. This is an example of one of our masks with about 400 4-channel multiplexer devices. The graph on the right shows the expected spectra from each one of these multiplexers. Now, optical chip testing is a very expensive and very time-consuming process. It requires dicing a wafer into individual chips or bars to allow access to the chip inputs and outputs for optical coupling, and then individually aligning fibers to the chip to obtain the transmission spectra. Therefore, to characterize a single wafer is typically a multi-day effort. We have decided to tap into the power of machine learning to develop an alternative to this arduous and expensive process of optical chip testing. So we developed a new technology that relies on a wafer probe to collect metrology data from multiple locations on the wafer. The collected spectra shown here are very noisy and extremely weak. And the challenge is to use these weak spectroscopic signatures to predict the performance of devices whose spectra look distinctly different. Not only that, but we want to predict the performance of hundreds of such devices on a wafer, where the pass and fail of each chip is determined by a long list of 26 specification parameters. So each channel within each chip is characterized against insertion loss spec and detuning spec, multiple passband specs, crosstalk, and so on. So essentially, our goal is to take this limited set of weak and noisy spectroscopic signatures and predict the performance of hundreds of devices on the wafer. The complexity of this problem absolutely necessitates the use of machine learning. Conveniently, though, the challenge of finding correlations within weak and noisy signals maps to one of the strengths of machine learning algorithms. So we've developed a support vector machine that allows us to do nonlinear binary pass-fail classification based on the probe data. So this is an example of one of our wafers. The spectroscopic signatures collected by the wafer probe allow us to construct a prediction map. So the colors here represent the pass-fail, or rather the predicted pass-fail of individual chips. Orange represents a predicted fail. So we predict that the chip will fail the list of 26 specification parameters, and the green represents a predicted pass, while the colors in between indicate the degree of confidence of the measurement. Well, how does this compare to reality? Well, to obtain training data for our support vector machine, we still need to measure some of our wafers using traditional means. So this is the exact same wafer, but this time it was individually diced and each one of the chips was individually measured. And here again, you can see the pass-fail of the individual chips, but this time based on an actual measurement. So you can see that our model accurately predicts the bad and the good portions of the wafer, which allows us to direct our resources accordingly. Now, compared to the multi-day effort that it takes to measure a single wafer, the total time that it takes to mount, align, and collect the spectroscopic signatures is only 12 minutes. And the inference from the SVM is instantaneous. Now, besides the obvious economic advantage of this approach, there is another advantage. Because the wafer remains intact, it remains in its undiced form, we are able to do in situ monitoring of our fabrication process and introduce process adjustments as required. This gives us an unprecedented control over the fabrication process, allowing us to produce consistently high-performing wafers at large production volumes. To lead us into our second example of a classical machine learning technique, we will first talk about ensemble learning. In some cases, an aggregated answer from 1,000 random people is better than an expert's answer, and this is known as the wisdom of the crowd. Similarly, if we aggregate the predictions of a group of predictors, we will often get better predictions than with the best individual predictor, and that's the main idea behind ensemble learning. Surprisingly, even if each predictor is a weak learner, barely better than random guessing, the ensemble can still be a strong predictor, provided there is a sufficient number of weak learners and that they're sufficiently diverse. So ensemble methods work best when the predictors are as independent from one another as possible. This increases the chance that they will make very different types of errors, improving the ensemble's accuracy. Now, inference of an ensemble is done by collecting the votes of the individual predictors in a process called aggregation. One way to achieve a diverse set of individual predictors is to train each one of them using very different algorithms. Another way is to use the same algorithm for training, but to train them on different random subsets of the training set. Random forest is a popular ensemble learning method. A forest is composed of many decision trees that form the ensemble tree. Now, a decision tree is a machine learning algorithm that can perform both classification and regression tasks. It's a white box model, meaning that it's intuitive and its decisions are easy to interpret. But the problem with decision trees is that they tend to be very sensitive to variations in the training data. However, decision trees can act as very effective fundamental components of random forests. Now, a random forest, as you might have guessed, is an ensemble of decision trees. Random forests introduce randomness when growing or constructing the individual trees, so that we have a greater tree diversity and thus better accuracy of the ensemble. Now, unlike decision trees, random forests are much less sensitive to noise and variations in the training data. They're also highly efficient for large data sets, and they're very popular machine learning model because they have fewer parameters compared to other machine learning algorithms. This is an example where a random forest was used to improve both the accuracy and the range of a vector displacement sensor. The sensor was constructed using a multi-core fiber inscribed with Bragg gratings. The fiber Bragg grating response was recorded from 4 cores, the central core, which was used for temperature compensation, as well as 3 outer cores. By measuring the Bragg wavelength shift in the different cores, both the direction and the amplitude of the displacement can be determined simultaneously in a 2-dimensional plane. However, the theoretical model that relates the Bragg wavelength shift to the displacement is limited in accuracy to a very small range of displacements. To overcome this limitation, this group trained a random forest with 100 diverse regression trees. The model's prediction of the direction and amplitude of the displacement was constructed based on averaging the predictions of the individual ensemble members. Now, the ability of the random forest to handle nonlinear regression effectively means that we are no longer limited to the linear regime of the system, allowing the setup to achieve much better performance both in terms of the measurement range and the accuracy. So these were 2 examples of classical machine learning architectures. And now we will switch gears and talk about artificial neural networks and deep learning. Modern deep learning architectures are based on neural networks, which are inspired by the learning patterns in biological nervous systems. Recent increase in computing power made it possible to train large-scale neural networks in a reasonable time. This increase in computing power came from Moore's law, but also from production of powerful GPU cards thanks to the gaming industry, as well as cloud platforms that make this computing power available to anyone. Biological neurons produce short electrical impulses called action potentials that travel along the axons and make the synapses release chemical signals called neurotransmitters. When a nearby neuron receives a sufficient amount of these neurotransmitters within a few milliseconds, it fires its own electrical impulses. Such neurons are often organized in consecutive layers. And the key idea here is that while each individual neuron behaves in a simple way, a vast network of neurons can perform highly complex computations. In the world of AI, the equivalent of the biological neuron is the artificial neuron, also called TLU, Threshold Logic Unit. It computes a weighted sum of its inputs and outputs the result of an activation function to the sum. Now, similarly to biological networks, an artificial neural network is composed of multiple layers of artificial neurons, each performing a certain transformation on its input. With the combined transformations throughout all the layers, the neural network is essentially capable of representing arbitrary real-valued functions. Now, an important question is, why is activation function required? Well, if you chain multiple linear transformations, you still get a linear transformation. Equivalently, if you don't have some nonlinearity between the layers, even a deep stack of layers is equivalent to a single layer. Conversely, a large enough neural network with nonlinear activations can theoretically approximate any continuous function. Now, the artificial neuron is used as a building block for the artificial neural network, which consists of an input layer, one or more hidden layers, and an output layer. We call a network fully connectorized if each neuron is connected to every other neuron in the adjacent layers, and we call a network a deep network if it has more than a single hidden layer. Now, when an artificial neural network is learning, it iteratively refines its internal representation by reinforcing those connections that lead to more accurate predictions and reducing the weights of those that do not. And that helps it achieve better predicting power over time. But how are these individual weights adjusted? Well, the two fundamental algorithms that underlie the learning process of neural networks are gradient descent and the backpropagation training algorithm. Gradient descent is a generic iterative optimization algorithm that is capable of finding optimal solutions to a wide range of problems. Its main idea is to measure the local gradient and then keep going in the direction of a descending gradient. So here's an intuitive analogy. Suppose you're lost in the mountains and the fog is so dense that you cannot see anything around you, but you can only feel the slope of the ground below your feet. So a good strategy to get to the bottom of the mountain is to go downhill in the direction of the steepest slope. And this is exactly what the gradient descent does. If we graph the same concept, then we start with some random value of the initial weight, and then we improve it gradually at each learning step, attempting to decrease some cost function until the algorithm converges to a minimum. This approach of using gradients to drive optimization is used extensively in nanophotonic inverse design. This is work done at Stanford University with their inverse design software package called SPINS. SPINS uses the gradient, or specifically the sensitivity of the loss function with respect to changes in the permittivity distribution, to guide the optimization process of photonic geometries. This allows them to explore a much larger fraction of the design space than is possible through traditional methods and construct these fascinating looking structures. This is a demultiplexer on the left, and this is a polarization splitter on the right in very compact footprints. But of course, in practice, it might not be as simple as it is depicted here. You can imagine that if the learning step size is too small, it might take an unreasonably long time to reach the solution. Conversely, if the learning step is too large, we may oscillate around the minimum, causing the algorithm to diverge. Also, not all cost functions will look like the nice bowl shown here. So depending on the random initialization, the algorithm might converge to a local rather than global minimum. These are the reasons why training machine learning models is often not straightforward. However, these challenges notwithstanding, gradient descent underlies the backpropagation training algorithm that is at the core of training neural networks. The backpropagation algorithm consists of 4 steps. First, starting from a random initialization of all the weights in the network, we compute the output of each one of the neurons, preserving the intermediate results. When the pass reaches the output, the algorithm can calculate the network's output error. So for example, that could be the mean square error between the target value and the value obtained from this forward pass. Now, recall that each of the neurons is a mathematical function. It's just a weighted sum of the inputs plus an activation function, which means that each point in the network is a well-defined mathematical function. So the algorithm can compute how much each output connection contributed to the network error. This is done analytically by applying the chain rule and computing the partial derivative. The same can be done to figure out how much of these error contributions came from each connection in the layer below, and so on, working backwards until we reach the input layer. In other words, this backwards pass measures the error gradient across all the connection weights in the network. And finally, the last step is the gradient descent step. The algorithm performs the gradient descent calculation to tweak all the connection weights in the network using the error gradient it just computed. So let me repeat that once again. For each training instance, the backpropagation algorithm first makes a prediction, preserving all the intermediate results. It then measures the network error, and then goes through each layer in reverse to measure the error contribution from each connection. And then finally, all the weights in the network are tweaked to reduce the network error, and that's the gradient descent step. By iteratively repeating this process, the artificial neural network gradually converges to a state where it can make accurate predictions based on the input data. To illustrate the process of actually training a neural network, we will look at another example from our work at Ensemble that deals with fine-tuning the design of photonic chips. In any fabrication process, some variation of physical parameters is inevitable. This includes variations of physical parameters within a wafer, as well as the difference between wafers and between different batches of wafers. Now, traditionally, standard statistical methods are used to compensate for such systematic process non-uniformities. This approach is based on deriving some physical or spectral characteristic of the devices, averaging it out over many wafers, and then compensating for it in subsequent iterations of the mask. However, this traditional approach has two limitations. First, it requires the judgment of a human, and thus is usually restricted to handling low-dimensional data. And second, it can compensate only for a limited set of already known dependencies, while not being able to capture dozens or hundreds of chip-specific dependencies that may not have yet been discovered. Machine learning offers an entirely new approach for addressing this problem. In fact, the high dimensionality of the fabrication process and the chip performance data is ideally suited for deep neural networks that are capable of deducing complex relationships between the design parameters, fabrication recipes, and ultimate chip performance. We use a deep neural network to study the variability in performance of individual chips, and then, once the model is trained, to predict the adjustments required to compensate for such variability in the design of a production mask. This is a multivariate regression problem where the device spectrum is correlated to the device parameters. Shown here is an example of the data used to train the model for the prediction of optimized design parameters of a 4-channel multiplexer. This is a supervised learning strategy, and each of the training instances is a normalized spectrum generated through simulation, while the label consists of 18 design parameters that are used to construct a multiplexer device. Our training dataset consists of 900,000 training instances, with about 1/10 of it reserved for the validation set. And we use a standard iterative approach to validate the model until maximum accuracy of prediction is achieved. Now, once the model is trained, we can feed a measured non-ideal spectrum to the model and use it to infer the vector of 18 design parameters that characterize this particular multiplexer chip. The difference between the inferred parameters and the intended design parameters is captured for each individual chip on a wafer, and we can use this chip-specific difference to compensate for the systematic process variation in a new version of the mask, with the goal of achieving a highly uniform performance. So let's look at the actual results. Although the devices in the initial mask were designed to be identical, we observed that these devices have large variations in their performance. So here is an example of a high-performing chip, and this is an example that is nominally identical but is performing quite poorly. And although this does not happen often, it is also not an isolated case. In contrast, the devices that were manufactured based on the ML-enhanced version of the production mask show consistently high performance over hundreds of devices on a wafer. This human-machine collaboration, where a human designs the optical chip and ML is used to fine-tune the design parameters, results in outstanding uniformity of performance of mass-produced photonic chips, despite our imperfect control over the fabrication process. Now, but what can you do if getting a large enough data set is simply impractical? Well, one approach is to use synthetic data. So in this example, our entire training data set of nearly 1 million spectra was obtained through simulation. But that's not possible in all cases. Think, for example, about 3D FDTD simulations and having to obtain 1 million of them. That's not practical. It's even more difficult for experiment, since it might actually require you fabricating and measuring hundreds of thousands or millions of samples. So in these scenarios, there are two additional approaches that can be considered. The first one is data augmentation, and the other one is transfer learning. Data augmentation is a technique that allows one to artificially increase the size of the training set by creating modified or augmented versions of existing data samples. These generated instances should be as realistic as possible. Ideally, given an image from an augmented training set, a human should not be able to tell whether it was augmented or not. This is an example where various transformations were used to augment the data set of MRI images of brain tumors. In essence, for every original MRI image, 7 additional images were generated using various transformations. Now, in addition to increasing the size of the training set, data augmentation also forces the model to be more tolerant to slight variations in the images, like the exact positioning, rotations, the size of the object, the light conditions, and so on. Similar techniques can be used for non-image data sets as well, and the key idea remains the same: to introduce controlled and realistic variations to the data while preserving its underlying structure and meaning. Transfer learning is a machine learning technique where knowledge gained from training a model on one task is applied to improve the performance of a model on a different but related task. Especially for very large neural networks, it is often preferable to not start training from scratch. So the idea of transfer learning is to try and find an existing neural network that accomplishes a similar task and reuse the lower layers of this network. Transfer learning does not only speed up training, but it also requires significantly less training data, because in essence, you're training a much smaller neural net. Transfer learning is particularly useful when the source data set is large and inexpensive, and the target data set is small and expensive. This is an example where transfer learning was used to migrate knowledge between different physical scenarios of multilayered structures. The overall setup was the following. They considered a source network, which was a fairly standard neural network with 6 hidden layers, and it was learning from a fair-sized data set of about 500,000 instances. And then they considered a target network, which reuses the first n layers from the source network and then trains on a very small data set of only 500 instances. Transfer learning was investigated in the context of 2 different scenarios. First, the transfer of knowledge between 2 similar physical problems. So here the source task was a transmission from a 10-layer film, and the target task was a transmission from an 8-layer film. And in the second scenario, the transfer of knowledge was done between 2 very different physical problems. where the source task was scattering from an 8-layer nanoparticle, and a transfer of knowledge was done to a transmission of an 8-layer film. The authors look at the errors in the prediction of the models when different combination of layers were transferred from the source network to the target network. And they compare these errors to direct learning based on a limited data set of 500 samples. So the results confirm that while some layers are task-specific, others are general to both problems. And this suggests that selectively transferring layers can effectively enhance the target performance of various kinds of multi-layered structures, even when the training data is severely limited. Now, although most of today's machine learning applications are based on supervised learning, the reality is that the vast majority of the available data is unlabeled. The key realization here is that our ability to learn effectively from unlabeled data is crucial to alleviating our dependence on supervised learning in many types of problems. In these circumstances, unsupervised and semi-supervised learning strategies can be used to reduce or eliminate the need for extensive data collection. In this context, we will briefly talk about the transformer network architecture. The most prominent application of this architecture is ChatGPT, and its fame is well justified due to its revolutionary effect on various natural language processing tasks. The transformer network architecture in its simplest form can be described as a deep neural network that incorporates two key components: an attention mechanism and positional encodings. The attention mechanism encodes each word's relationship with every other word in the same sentence, paying more attention to the most relevant ones. This allows the model to capture long-term dependencies and complex relationships between different parts of the input. Meanwhile, positional encodings provide information about the order and position of words in a sentence, ensuring that the model understands the sequential nature of the data. Now, the transformer architecture was first introduced by the Google Brain team in a seminal paper entitled "Attention is All You Need." In this paper, they demonstrated that the attention mechanism, when combined with positional encodings, could very effectively model complex relationships between words in a sequence, surpassing the performance of traditional models. The next important paper on the subject came from the OpenAI team less than a year later. They explored a semi-supervised approach for language understanding tasks. Their semi-supervised approach consisted of two distinct phases. The first one was unsupervised pre-training, and the second one was supervised fine-tuning. Now, during the first unsupervised pre-training stage, the model is trained on a massive corpus of unlabeled data with long stretches of contiguous text. During this stage, the model learns to predict the next word in a sequence given the preceding context. By modeling the language in this way, the model becomes proficient at generating coherent and contextually relevant text. Through this learning, the model acquires significant word knowledge and the ability to process long-range dependencies. Then, in the second supervised fine-tuning stage, supervised learning is used to adapt the parameters of the pre-trained model and transfer the learned abilities to specific target tasks, such as question answering or text classification. In essence, this fine-tuning stage leverages the general language understanding abilities of the pre-trained model while tailoring them to the nuances and requirements of the target task. This model, that is known as GPT, Generative Pre-trained Transformer, is a foundational model. In other words, it's an AI model that was trained on broad data at scale, such that it can be adapted to a wide range of downstream tasks. Now, since 2018, the transformer network was extended and adapted for many other applications besides natural language processing. This is very recent work from the University of Michigan, which reported progress towards building a GPT model for inverse design of optical multilayered thin film structures. Similarly to ChatGPT, which generates its outputs autoregressively, meaning one step at a time in a sequential manner while taking into account the previously generated tokens. Their OptoGPT model generates multi-layered structures layer by layer in an autoregressive way. The inputs to the model consist of optical targets that are formulated as reflection and transmission spectra. And the outputs are sequences of tokens that represent design multilayered structures. This model can also be considered foundational model because it can be used for the design of optical multilayered thin films across a diverse array of applications like filters, distributed Bragg reflectors, absorbers, and so on. The last topic we will discuss today is reinforcement learning. If you recall our previous discussion, it is a branch of machine learning that is inspired by the concept of learning through trial and error. When an agent is learning, it continuously updates the connection weights of its deep neural network using the gradient descent optimization algorithm. These adjustments result in gradual improvements in the policy employed by the agent. This is an example of work that employs reinforcement learning for routing in underwater optical wireless sensor networks. Unlike more typical distributed networks, these networks are subject to two major constraints. First, dynamic and unpredictable changes in the network topology, which is caused by the movement of individual underwater nodes. And second, severe energy constraints. Because of these unique limitations, traditional routing protocols lead to poor performance. And in fact, even if we were to deploy reinforcement learning on each of these nodes, so each node acts as an independent agent that explores its environment, that still leads to poor performance. Now, one of the biggest challenges in reinforcement learning is defining what would constitute a meaningful reward. Ideally, the reward should capture the objectives and the goals of the task, guiding the agent towards desired behaviors and away from undesirable ones. So the approach taken in this work is to deploy a multi-agent reinforcement scheme, where the agents learn not only from the local rewards for communication between the immediate nodes, but also global rewards that give them a global perspective of the network. Now, the local reward was defined as a function of two parameters, the link quality and the residual energy. This means that not only that every agent takes an action that maximizes the chances of the communication getting through, so that's the link quality parameter, but also that the next hop in communication is likely to go through a node with more residual energy. This ensures better balance of the network energy, encouraging high-power nodes to be more active and gradually reducing the load on low-power nodes. Now, as for the global rewards, ideally every node has full awareness of the state of the network. But for this to be possible in a highly dynamic network, there's a lot of communication that is required between the different nodes. And since energy conservation is one of the biggest constraints of underwater networks, that's not a feasible solution. So the global reward chosen in this work was actually quite simple. It's a positive reward if a message manages to get one step closer to the sink or the target, and it's a negative reward if it did not. The combination of these local and global rewards is an effective way to enhance the likelihood of successful communication while also maintaining a balanced network load, thereby extending its operational lifespan. And with this, we will wrap up. To conclude, allow me to give you a visual rundown of the past hour's highlights. Because unlike machines that may scratch their neural nets trying to make sense of an image, for us humans, an image is worth 1,000 words. Machine learning is a wide topic whose landscape is constantly changing. We talked about the three broad categories of machine learning: supervised learning, unsupervised learning, and reinforcement learning. We talked about deep learning, that it is a data-hungry method that can only work well if fed with massive amounts of data. The biggest challenge in training deep neural networks is overfitting. We can fit an entire zoo. We talked about the no free lunch theorem, that there is no one-size-fits-all machine learning algorithm that performs optimally across all possible problem domains. In many cases, rather than spending time and resources on algorithm development, it may be worthwhile spending these resources on improving the quality and the quantity of the training data. We talked about two powerful classical machine learning algorithms. First, a support vector machine and how it was applied to predict the performance of hundreds of chips on a production wafer based on a wafer probe measurement. We talked about ensemble learning and a particular example of a random forest and how that was used to improve the performance of a vector displacement sensor. We talked about the basic functionality of a biological neuron and its equivalent in the world of AI, the artificial neuron. We talked about the gradient descent algorithm and how it is used to drive optimization in nanophotonic inverse design. We talked about artificial neural networks and how they were used to achieve exceptional uniformity of performance for mass-produced photonic chips. We talked about the idea of transfer learning. Especially for very large neural networks, it is often preferable to find an existing neural network that accomplishes a similar task and reuse the lower layers of this network. And we saw how this was successfully applied to the study of various multilayered structures. We talked about the burden of data collection and how it can be alleviated by the use of unsupervised and semi-supervised learning strategies. In this context, we talked about the transformer architecture and its most famous example of ChatGPT, as well as a conceptually similar setup used for inverse design in optical multilayer thin film structures. And we talked about reinforcement learning and how a multi-agent reinforcement learning scheme was used to develop an efficient routing algorithm for underwater optical wireless sensor networks. And lastly, the photonics technology has a great potential to revolutionize the capabilities of many of today's key technologies. And I hope the past hour has shown you that AI and machine learning give us a powerful new toolkit for accelerating this progress. Thank you to my colleagues at Enablance who spent many hours discussing these concepts, Serge Bidnick, Ashok Balakrishnan, and Todd Newen, as well as the young and talented artist by the name of Neo who helped me illustrate parts of this presentation. Thank you all for your attention.